So the physical system that we were investigating consisted of a mass which was connected to a wall using a spring. There was also a damper attached to the mass and a transient force function acted on the mass. So transient means something that depends on time. So we started by writing the Newton's second law of motion. So any equation of motion is a specific form of Newton's second law of motion, right? So any equation of motion would start by writing F equals to ma, and then you will add the details, then you will get a specific equation. Now in this particular instant, the equation that we obtained was m the second derivative of x with respect to time plus c dx dt plus kx equals to ft, where x is the position of this mass measured from the wall. This is x. So this is the second order differential equation because the highest order derivative is of the second order. So it takes the name after the highest order derivative. Then we talked about how this can be solved. So this can be solved by substituting a model solution, right? So in this case, we substituted x equals to a e to the power lambda t, and upon substitution, we got an equation, and we call this equation characteristic equation. So the equation that we obtained was lambda square plus c over m lambda plus k over m equals to 0. And this is a quadratic equation, and as you know, the quadratic equation has two solutions. Okay, and the solution to this equation is equal to, so there are two solutions, lambda 1 is one solution and lambda 2 is another solution, and it is minus c over 2m plus minus square root of c over 2m square minus k over m. And then we discussed the various possible solution behaviors depending on how this c over 2m compares with square root of k over m. So we discussed three possible cases. Now in all these three possible cases, c, which is the damping coefficient, right? So this c is called the damping coefficient. It's the damping coefficient. So in the three cases that we first described, we assume that there is a positive damping, means this is going to oppose the motion. It will damp out the motion, means it will slowly bring the motion to a halt, meaning it will get rid of the motion. Okay, so it will slow down the mass with time. So we assumed a positive damping coefficient, and we discussed three scenarios. Number one was c over 2m is greater than square root of k over m, and in this case the solution was found to be real and negative. And when the solution is real and negative, we analyzed the function, the solution function, and we concluded that it will lead to an overdamped motion. So there are no oscillations, but the motion will just monotonically decay. And actually, to see that, you'll have to look at the general form of the solution. So the general form of the solution, now I'm stepping back a little bit. The general form of the solution was x of t equals to c1 e to the power lambda 1t plus c2 e to the power lambda 2t. where the constants C1 and C2 will be determined from the initial conditions. So as I was saying now, if C over 2m is greater than square root of k over m, we get an overdamped motion, a monotonically decaying motion, so there are no oscillations. The second possibility was C over 2m is less than square root of k over m. And in that case, you can imagine that under the square root, we'll have something negative, which means the solution to lambda will be imaginary. It will have a real component and it will have an imaginary component. So in this case, because of this imaginary part, the solution will represent an oscillation. Okay, so the solution will contain sines and cosines, and the real part of lambda is going to make the amplitude of the oscillation decay with time, whereas the imaginary part will make the motion oscillatory. And in this case, the oscillation frequency is equal to k over m minus c over 2m square. This is the frequency of oscillation, and the decay of the oscillation amplitude is controlled by the real part of the solution for lambda, okay, or in other words, c over 2m. And the third case scenario was when c over 2m is equal to square root of k over m. And in this case, we have only one value of lambda, and this value of lambda is just going to be equal to minus c over 2m. So in this case, lambda is equal to minus c over 2m, and as you can imagine, if you substitute it in the equation for x, so if you put minus c over 2m here, you put minus c over 2m here, it will produce an exponentially decaying function, and this is called critically damped motion. And I think we stopped somewhere around here. First, I'm going to now continue with this critically damped case where c over 2m is equals to square root of k over m. Now, in this case, let me write an expression for c. Okay, so c is equal to 2m square root of k over m, which will give me 2 times square root of km. So this c equals to 2 square root of km. This 2 times square root of km, this is called the critical damping constant. Okay, so this is symbolized by CR, and it is called the critical damping constant. So the idea is that any C can be expressed in terms of this critical damping coefficient. So I can write C as C equals to C divided by CR times CR. Okay, and the reason why we are doing this will become clear in a little bit. But first, let's just recognize that we can do this. We can write C equals to C divided by CR times CR. CR will cancel, C will be equal to C. And this ratio of the damping constant or damping coefficient to the critical damping constant or critical damping coefficient, this ratio is known as the damping ratio. So C over CR is called damping ratio. And it is represented by the symbol zeta. So we write C over CR equals to, this is called zeta. This is a Greek letter. So that we can write damping coefficient equals to damping ratio times the critical damping constant. And now, instead of thinking in terms of the damping coefficient C, we can think in terms of the damping ratio. Okay, so very soon I'm going to rewrite this equation in terms of the damping ratio. So I'm going to substitute for C. Okay, I'm going to write it in terms of damping ratio. You'll see that soon, and there is an advantage of doing that, as it will become clear in a little bit. So if you go back to the second case where we had an oscillatory behavior, there was a frequency associated with that solution, this one. So this is called the frequency is called the damped natural frequency. It's called the damped natural frequency. Now we can define another term here when C equals to 0, or when the damping ratio is equal to 0, or when the zeta is equals to 0, right? So if you look at the definition for damping ratio, it is C over CR. So when C equals to 0, this damping ratio equals to 0, or the zeta equals to 0. Okay, so when the damping ratio is equal to 0, we get omega equals to square root of k over m. And this square root of k over m is called the natural frequency. So this is the frequency when there is no any damping. So in other words, the amplitude of the oscillation will remain constant. It will neither grow, it will nor decay. The amplitude of the oscillation will remain constant in this case. And this square root of k over m is written as omega n, where n represents natural frequency. So now we are ready to write the second order differential equation in terms of the damping ratio and the natural frequency. So let's do that, and you will realize that it turns out to be a very meaningful representation of the second order differential equation. So the equation we have is this one. Now I'm going to divide all the terms by mass, and then that will give me second derivative of position with respect to time plus C over m dx dt plus k over m x equals to 1 over m ft. And our goal is to now write this equation in terms of zeta and omega n instead of c, m, and k. So let's see how we can make those substitutions. So look at this and look at this. It is clear that k over m is equals to omega n square, right? So from here we know that k over m is equal to the square of omega n, which means instead of k over m here, I'm going to write omega n square. Now what about this c over m? So it turns out that the c over m, okay, so I'm going to just show it here. The c over m can be written as 2 times zeta times omega n, and let's prove that to ourselves. So this is 2 times zeta, which is c over cr, times omega n. Omega n is square root of k over m. Right, square root of k over m. And remember that what is this cr? Cr is 2 times square root km. So we have 2 times c divided by square root of km times k divided by m. Now the square root of k get cancelled. And we get, so square root of m times square root of m will give us m, get c over m, right? So in this way, you can show that c over m is equal to 2 times zeta times omega n. So here, this c over m can be written as 2 times zeta times omega n. And this ft divided by m will just be written as a function of time, okay, which means the second order differential equation for this mass on a spring can also be written as d square x dt square plus 2 zeta omega n dx dt plus omega n square x equals to f of t. And the reason this is a more meaningful form is this now helps us to directly know something about the solution just by looking at the equation. You look at the equation, you find the coefficients, and then you can just know what will be the frequency of the system. You will know what will be the value of damping ratio. So that will tell you how the amplitude of the oscillation will decay. Okay, so just by writing the equation in the proper format in this way, you will know so many things or important things about the solution. Okay, that is the reason we converted this general form of the second order differential equation into this particular form. So not just this equation, even now this characteristic equation can be written in terms of the damping ratio and natural frequency. So what was our characteristic equation? The equation for containing lambda. This was the characteristic equation. So here also we can substitute. So instead of c over m, right, instead of c over m, we can write 2 times zeta times omega n. Instead of k over m, we can write omega n square. Okay, so that this equation can be written as lambda square plus 2 times zeta omega n lambda plus omega n square equals to 0. And not only that, even the solution for this lambda, which contains, you see, c over m, k over m, so even this can be written in terms of omega n and zeta, and we should do that. Okay, so when you actually make the substitution and simplify, you will get lambda 1 2 equals to minus zeta times omega n plus minus I omega n square root of 1 minus zeta square. So in this way, the real part is, so the real part of lambda, real part is minus zeta times omega n, and again this is represented by eta, and this eta, as we have already talked, okay, this governs the decay rate of the amplitude. Okay, so what did I say when we were talking about the second case? We said that there is a real part and then there is an imaginary part. The real part controls the rate of decay and the imaginary part controls the frequency of oscillation, right? So I'm repeating the same thing. So the real part, which is eta now in the new notation, it controls the rate of decay, and the imaginary part, which is omega n, this is the frequency. Okay, so this is the damped natural frequency. So this is the same as this, and you can show that to be the case. Okay, so these two are same. If you make the substitution for k, m, c, m, okay, in terms of zeta and omega n, you will get this expression. So in this way, later on, now this type of representation is going to be useful when we represent the solution in a complex plane. It is going to be useful, which is the reason we are defining all these new variables. So the conclusion, at least for now, is that the second order differential equation can be written in terms of the natural frequency and the damping ratio. Okay, and we now have these new variables eta and omega, which will be used later on to represent the solutions in the complex plane. And just like we talked about the different scenarios in terms of comparison between c over 2m and square root of k over m, now we can talk about different scenarios in terms of this eta and omega. Okay, so we can talk about the different scenarios in terms of eta and omega. I will not go into those details today. If we have time remaining on Monday or Tuesday, I can revisit this. But basically, we will be repeating the same discussion we had when we talked about the different solution behaviors as in case 1, case 2, and case 3, but we will just be narrating the same story in terms of eta, in terms of different range of values of eta. And this has been summarized in table 4.1 of the book. So for now, after the class, you can have a look at that table if you are interested in this. And if we have time, we can talk about it again next week. Okay, so this is, so read table 4.1. So now we will try to apply what we have learned. So as I had said before we started this topic, we are going to learn about the general behavior of the solutions of the second order differential equation, and we are going to use it in some aircraft related physical scenario. Okay, so we talked about this in the context of mass on a spring, but now we will talk about it in a more aircraft related context. We had two sets of equations of motion. One was the equation for moment, which is this set, and there was an equation for force, which I have not written. And then, if you recall, in that chapter, what we did was, from these equations of motion, we obtained the equations for small perturbations, right? So we basically applied the small perturbation theory. In other words, we substituted the perturbed variables. So for instance, instead of writing L, we said L equals to L naught plus delta L, sorry, and M equals to M naught plus delta M. And that is the case when there is a small disturbance, right? So the value of L naught changes to L naught plus delta L. So we substituted it in these equations, and then we opened the brackets, we linearized the equation, which basically means we got rid of higher order terms, which are very small, right? So for example, delta L times delta Q, or delta P times delta R, things like that we threw away. And then we obtained a set of equations, and we said that we have to solve those final equations to understand how these perturbed quantities evolve with time, right? How do they become zero again? How does the aircraft come back to the equilibrium state? So this is what we said at that time. And that is fine. This is what has to be done in all cases. Now, another approach is, which is actually a simplified version of what I just described, is instead of obtaining a very general solution, what we can do is we can start being specific right from this step. Okay, for example, let's say the aircraft is only allowed to pitch and it is not allowed to do any other type of motion. Okay, so in other words, you think about your wind tunnel. So this is the wind tunnel, and you have mounted the aircraft on this stand. So since this aircraft is mounted on the stand, you cannot move it left, right, you cannot move it up, down, you cannot move it out of the board or into the board. It is fixed in its location. And let's assume that it has been mounted on this stand in such a way that it is only allowed to pitch up and down. So only the pitching motion is allowed. Okay, so this type of motion is known as pure pitching motion. So this is pure pitching motion. Other types of motion, not possible. So let's try to solve the equation of motion for the case of pure pitching motion. So our approach is going to be same. We are again going to substitute the perturbed form of the variable into this equation, and then we are going to solve. Okay, we are going to solve means particularly we are going to find the oscillation frequency and damping ratio for that motion. Okay, this is what we will find, and that is very important, right? Because once you have the damping ratio and the frequency, then you can obtain the solution. You can obtain the solution, right? Because the solution is written. See, the solution is written in terms of lambda, and lambda is written in terms of the damping ratio and natural frequency. So if you can find the damping ratio and natural frequency, then you would have found lambda, and once you find lambda, you find the solution, how the variable is changing. Okay, now the variable could be position, it could be angle, anything. Now you can already guess that in a pure pitching motion, since only the pitching is allowed, we will be solving for how the change in the angle of attack evolves with time. So instead of xt, we will be finding delta alpha t, right? So how the angle of attack. So let's say the aircraft is at a particular angle of attack, and because of a gust of wind, the angle of attack changes. So now how does this change? How does delta alpha evolve with time? This is what we will be interested in knowing in this process. Okay, and obviously if we are going to do all this, then we need to write the given equations in the form of a second order differential equation. So in other words, we need to write the aircraft equation of motion for the pure pitching motion in this format. So how do we bring the equation into this format so that we can learn, or so that we can use what we know about the second order differential equation? Okay, so in this way, you need to connect what you learned in aircraft's equation of motion with what we have learned about the second order differential equation. You need to make this connection, and I'll show you how that will happen. So first thing to note, again, to emphasize, is that this is a pure pitching motion, means only motion about the y-axis is allowed, right? So if you imagine the aircraft, this is the x-axis and this is the y-axis, right? This is the z-axis. So we are only letting the aircraft pitch up and down, means only movement or rotation about the y-axis is allowed, which already means that we don't care about moment about the x-axis and moment about the z-axis. These equations go away because there is no any moment about the x and z-axis. There is only moment about the y-axis, which represents the pitching moment, and so only this equation is going to remain. Okay, so already the math is significantly simplified. Now we said that only pitching is allowed. So yawing and rolling are not allowed. Okay, so that means okay, so the angular velocity has three components, right? P, Q, and R. So P is the angular velocity about the x-axis, Q is the angular velocity in the y direction, and R is the angular velocity in the z direction. So if we are saying that only pitching is allowed, then P is 0 and R is 0. Only Q is non-zero, right? Because Q is the pitch rate. Okay, Q is the angular velocity in the y direction. So because of this, the second term is 0 because there is a P there which is equal to 0, and since both P and R are 0, this term is also equal to 0. So the equation that we are left with is M equals to Iy Q dot, and this is already very simple. Now we have talked about this in an earlier chapter, right? So we talked about the second law of motion applying only in the inertial frame, and then we wrote that second law of motion. Then we had made a substitution in the right hand side, and we converted the variables from the inertial frame to the body frame. This is how we got these equations. And now I'm talking about going back. Okay, so we need a way to convert this Q dot from the body frame to the inertial frame, and this is also covered in the book, although we did not discuss it in detail, but you can see this in equation 3.31 in the book. So if you go to 3.31 equation, it shows you how P, Q, and R can be converted into angles measured in the inertial frame. So how P, Q, and R can be converted into phi, theta, and psi. So phi, theta, and psi are the angles measured in the inertial frame of reference. These angles are called Euler angles. We talked about this before. Okay, Euler angles. So if you look at equation 3.31, so from equation 3.31, we know that q equals to plus cosine of theta sine of phi times psi dot. Now again, in this pure pitching motion, in this special case that we are analyzing, there is no any psi. Okay, so there is no any psi. Psi is the yaw angle, so it is equal to 0. The aircraft is not yawing, so this term goes to 0. And we are left with q equals to cosine phi times theta dot. And there is also no any bank angle, right? So the aircraft is not banking in this example. In a pure pitching motion, it can only move in the xz plane. It can only pitch up and down. So there is no any bank or yaw involved here. So phi is equals to 0. And when phi equals to 0, cosine phi equals to 1, right? So we get q equals to theta dot in this case. So that allows me to write m equals to iy q dot. And what is q? Q is theta dot. So this is theta dot and again dot, means the second derivative of theta. So I can write m equals to iy theta dot dot. So this is the equation of motion for a pure pitching motion. Okay, so this is aircraft equation of pure pitching motion. So it got very simplified. So we just have a one short equation. But we are interested in knowing how the disturbances evolve with time. Okay, so now what does that mean? We need to apply the small disturbance theory. We need to do something like this. In other words, we need to make substitution, right? So m is now equal to m dot plus delta m, and theta is equals to theta dot, sorry, theta naught plus delta theta. So you substitute that in this aircraft equation of motion. And again, I want you to realize that we have already done a more complicated version of this. Here I'm just applying the same process to a very simple case. So m becomes m naught plus delta m equals to iy, and theta double dot. What is theta? Theta naught plus delta theta. So second derivative of this, right? So double dot. So we have m naught plus delta m equals to iy. This is theta naught double dot plus delta theta double dot, means second derivative. Now m naught is the moment in the steady state. 0 naught represents the equilibrium, and we know that in equilibrium there is no any moment. Okay, in the trim point there is no moment. Trim point is defined by the condition in which the moment resultant moment equals to 0. Okay, so by definition this is 0. And also the aircraft in the steady state is maintaining a constant inclination. It is not changing with respect to time, means this is also by definition equal to 0. So the perturbed equation of motion that we get is delta m equals to iy delta theta dot dot. This is the equation that we obtain. And our goal is to write this equation in the form of this equation, so that we can immediately know what is the natural frequency, what is the damping ratio, what is the damped frequency of this aircraft. Okay, that is what we are trying to do. Now again, recall what we did in the aircraft equation of motion. After this step, we wrote delta m as a combination of stability derivatives. We are going to do the same thing here as well. So first of all, we will assume that this change in moment, so this is the pitching moment, right, is a function of change in the angle of attack change in the rate of change of angle of attack times change in the pitching frequency, or the y component of the angular velocity, times change in the elevator angle. So all these things will affect the value of pitching moment. Okay, there could be other things as well, but these are the most dominant variables which will affect the change in the pitching moment. So as I said, we will write this as a combination of stability derivatives. So I can write this delta m as dm d alpha times delta alpha plus dm d alpha dot times delta alpha dot plus dm dq times delta q plus dm d delta e times delta e. Now we will further simplify this by exploiting one of the characteristics of this pure pitching motion. So in the pure pitching motion, whether you measure the angles from the inertial frame of reference or from the body frame of reference, it will appear the same. And this will be enforced by saying that the body frames and the inertial frames coincide at the initial time. Okay, so we will say that the body and inertial frame, so coincide at t equals to 0 means they are on top of one another. Inertial frames coincide at t equals to 0. Just to make it less mathematical, you may just imagine that whether you are measuring the angle from the inertial frame or the body frame, in this particular case where the motion is only restricted to rotation in the xz plane, you're going to get the same value of the angle. Okay, so it will be the same. So this means the angle of attack change delta alpha will be equal to the change in the inclination angle. Okay, so both of these angles are being measured with respect to the x-axis, right? So this is the angle between the fuselage reference line, let's say, and the x-axis, and so both of them will be equal to one another. Okay, so when the two frames coincide at equals to 0, and when the motion is restricted to pure pitching motion. So that is one thing. And now I'm going to again come back to this we had obtained in the process of converting from the body frame to the inertial frame. So obviously this means that delta theta dot equals to delta q. Okay, so I'm going to bring it here and just copy it. Delta theta dot equals to delta q. So delta theta dot means delta alpha dot, right? So this is equal to delta alpha dot. Okay, right, so I'm going to use this and this. First, let me make a substitution for delta m in this equation. So this was our aircraft equation of motion. Then see, my goal here is to find how this delta alpha will evolve with time. So I want to know this. So is the angle of attack going to oscillate? Is the angle of attack going to monotonically decrease to 0? Is the angle of attack going to monotonically increase? Like, so how does this delta alpha evolve with time after it is disturbed? Okay, in this wind tunnel here, what is it going to do? Is it going to just oscillate, and then this oscillation going to just continue to grow? Is it going to oscillate at a constant altitude? Sorry, amplitude, not altitude. Is it going to, once it is disturbed, it will just monotonically decay, or will it just continue to increase? This is what I want to solve, which means I need to bring in that delta alpha into the equation, right? So I have to obviously make some substitutions now. So instead of this delta q, I can use this substitution. I can write delta alpha dot Okay, and what else can I do? I think that's it. Wait a second, I can also take care of this. Instead of this, I can just write delta alpha double dot, right? So I can write delta alpha double dot. So I have already done the background work to make those substitutions. So let me just rewrite the above statement as dm d alpha delta alpha. I'm going to take delta alpha dot as a common factor between these two terms. So I will have delta alpha dot dm d alpha dot plus dm dq plus dm d delta e. Well, there's nothing I can do about this elevator angle, equals to iy delta alpha dot. And you can now start to see this type of second order differential equation taking shape. Okay, this is where I'm moving, which is the reason I'm doing all this. So you can see that sort of appearance is developing here. Okay, so I'm going to move these two terms to this other side. Okay, I'm going to group it with iy delta alpha double dot, and so I will get iy delta alpha double dot minus, now let me write this term, minus dm d alpha dot plus dm dq delta alpha dot minus dm d alpha delta alpha equals to dm d delta e delta e. Okay, so still this has not appeared in the second order differential form that we want. In this form, it's still not there, and we need to do some more steps to bring it to that form. So divide all sides by iy. Okay, so we get delta alpha double dot equals to dm d alpha dot over iy. Oh, not equal. Not equal. So minus plus dm dq iy delta alpha dot minus dm d alpha iy delta alpha equals to dm d delta e iy delta e. And now I'm going to again define new variables. So this one will be written as m alpha dot, this one will be written as mq, and this is written as m alpha, and this is written as m delta e. So we have delta alpha double dot minus m alpha dot plus mq delta alpha dot minus m alpha delta alpha equals to m delta e times delta e. Now I should compare this with my previous equation. I should compare it with this form of the second order differential equation. So let me copy and write that equation so we can make the comparison easily. So we have a second derivative of x with respect to time plus 2 zeta omega n dx dt plus omega n square x equals to ft. So let me again use dots to rewrite this equation. So this would be x double dot plus 2 zeta omega n x dot plus omega n square x equals to ft. So what can we conclude? We can conclude the following. You can compare this omega n square with this. You can compare this with this. So what will be the natural frequency of this aircraft mounted in the wind tunnel, which is only allowed to pitch up and down? So the omega n is equal to square root of minus m alpha. Okay, and we have 2 zeta omega n equals to minus m alpha dot plus mq, and we know that omega n is equal to square root of negative m alpha. So we get this, and that means zeta is equal to minus m alpha dot plus mq over 2 times square root of negative m alpha. So this is the natural frequency. This is the damping ratio. And after you find them, you can also find the damped natural frequency. So the damped natural frequency, which is omega equals to omega n square root of 1 minus zeta square. So you can just make a substitution and you can find that. So to get a number, you will need to calculate m alpha dot, and mq, and then only you will get a number for this. And that will depend on the specific description of the problem. Okay, so we cannot just now start putting numbers, because we just said that the aircraft is free to rotate about the y-axis and other motions are restricted. So we only started with that as the given condition. So this is only as far as we can get in this particular case. Okay. So since we have omega n and zeta, we can find the lambda now. Okay, so we can find the real part of lambda. Again, go back to the equation and see, remind yourself of what was this lambda and why it was important. Okay, so see, this was the lambda, right? It had a real part, it had an imaginary part. So once we know this omega n and zeta, we can find the real part and imaginary part. So you can calculate this eta, you can calculate the damped natural frequency, and so you will get lambda, and after you get the lambda, you can plug in here. So now in this particular case, it will be delta alpha t, right? Because our dependent variable in that second order differential equation is the change in the angle of attack. So that will be equal to c1e lambda 1t plus c2e lambda 2t, and we will find the c1 and c2 from some initial condition that is given. So in this way, you will be able to find how this change in the angle of attack is going to change. Okay, so you'll just find how this disturbance will evolve with time. And we should discuss that more. We should make some plots of how the delta alpha should change with time. But I would like to postpone that discussion to the next week. Here I want to do something else. I would like to actually solve a numerical problem which allows us to apply these equations. Okay, this is what I want to do. And you will also be able to find this numerical problem in the book. And actually the book has redone these steps. Okay, so again, went through all the steps starting from the aircraft equation of motion, and then apply the small disturbance, small perturbation, obtain another equation, and then write that equation in terms of the second order differential equation, and then like obtain the values of omega and zeta. That is fine. That just reinforces these steps in your mind, and that sort of practice is very helpful when you face a new problem in the future. But for now, if we only want to see how these equations that we have obtained today can be useful, we can actually take a shortcut. And let me just describe. Now let me first explain what is happening here. So there is a rod here. Okay, at the end of the rod a plate is attached, and the rod is free to rotate up and down about this bar, this thin bar. The ballast just means a balancing weight. Okay, so this, you can imagine that it's a, let's say, a set of discs which can be slided along this rod to shift the center of gravity location. So the ballast is placed at the end of the rod in such a way that the center of gravity is here, is where the rod intersects with this horizontal bar. And you should assume that there is no any force of friction. So it says see low friction bearing, means you can ignore the friction. Okay, low friction bearing. And the various distances are labeled, right? And the size of the plate is also labeled. So you can imagine that this rod and the plate assembly can move up and down. It can rotate about this horizontal bar. Okay, so I'll be calling this line as rod, and I'll be calling this line as bar. So you need to find three things. You need to find the damping ratio. So you need to find this. You need to find the natural frequency. And then you need to find the damped natural frequency, this. Okay. Now there are two ways to do this. One is, for this particular problem, we repeat all the steps again. See, we already went through some steps of the analysis for pure pitching motion, and this is also pure pitching motion. This is also pure pitching motion, because this system is only restricted to moving by pitching. So the one possibility is we go through all that analysis again, and then we reach some point like this, and then we ask ourselves, okay, so what is the value of m alpha? What is the value of m alpha dot? What is the value of mq? Because we need that now for a number, right? And in this problem, we need to calculate a number. We need to calculate how many radian per second for the frequencies. We need to calculate a number for this damping ratio. This is one approach. It will not exactly be the same as what we are doing here, because this system, which is presented in this example, is even simpler than the pure pitch motion of an aircraft. How is it simpler? Because if this were an aircraft, what would have happened? If this were an aircraft, then we would have a wing, we would have tails, okay, and then free stream. So here also there is a free stream. So there is air blowing towards this assembly at u naught. And the system that is being considered in this example is simpler than this aircraft, because in the aircraft, it's like there are two wings, right? So there is this main wing, and then there is horizontal wings, vertical tails, things like that. Horizontal tails, vertical tails, I mean. But here that is not the case. So how does it simplify the process? If we were to do this whole thing again, we would have to neglect the dependence of the change in momentum on this delta alpha dot and delta elevator angle, because this system, which has been presented in the example, just a rod and a plate attached at the end, and this rod being able to move about this horizontal bar, this does not have an elevator. Okay, so delta m will not depend on delta E. And similarly, delta m, the change in moment experienced by this system, is not going to depend on the rate of change of angle of attack. In the aircraft, it does depend on rate of change of angle of attack, because see, by the time the air flows over this wing and reaches the vertical tail, it takes some time for the pressure distribution to rearrange, and then for the tail to respond to the airflow, right? So this all takes time. So that's why in the case of an aircraft with a wing followed by a horizontal tail, the moment also depends on the rate of change of angle of attack. But in this simple case, it will not depend on the rate of change of angle of attack. So actually, the full analysis will start differing from this step itself. So for the example that is given to us, we would be writing f is a function of delta alpha and delta e only. So that will remove some terms, and that really helps to simplify the problem. But today I don't have time to go through that route, so I'm just going to take a shortcut. What I'm going to do is I'm going to try to utilize the equations that we have already obtained. So we know that these are the two equations for a pure pitch motion, and I would like to directly apply that to obtain my answers. Okay, so fine, then no problem, right? So omega n will still be equal to square root of negative m alpha. That's good. I just need to find the value of m alpha. Now what about this damping ratio? Let me first copy it for the aircraft. For the aircraft, it is m alpha dot plus mq divided by 2 square root of negative m alpha. Now, as I already said, we don't have to worry about alpha dot, things changing with alpha dot, because there is no any alpha dot here in this problem. If there was another plate here, then maybe there would be an alpha dot, but that is not there. Okay, so this term is simply 0. And damping ratio is equals to minus mq divided by 2 square root of negative m alpha. All right. So I need to now, therefore, find the value of m alpha and find the value of mq. This is what I need to obtain a numerical answer. How am I going to do that? This is what I will describe now. The moment as a function of alpha is equal to so when the angle of attack will change, the lift force will change, right? So there will be a delta L generated on this plate, right? And that will obviously act at the aerodynamic center of the plate. Okay, by the way, don't get confused. This CG is the CG of the plate. It is not the CG of the overall system. The CG of the overall thing is here at the pivot. So when the angle of attack changes, the lift coefficient or the lift will change, right? This we also know from the airfoil data. And that extra lift will create a moment about the overall center of gravity. So the moment as a function of angle of attack is equal to negative times this L times the change in lift. And we know it is negative because an upward lift is going to try to turn this nose downward, right? So that's why we put a negative. But I said this is a function of alpha, and there is no any alpha here. But you should understand that the dependence on alpha is inside this delta lift. Okay, so this is equal to minus L. Now, what is the change in lift? Change in lift is, well, think about the definition of lift coefficient first. Lift coefficient is lift divided by half rho v square s. So lift is equals to half rho v square s cl. So change in lift equals to half rho v square s change in the lift coefficient. Okay, and what is this change in lift coefficient? Change in lift coefficient is equal to the lift slope with respect to alpha times change in alpha, right? And just to keep things simple in this process, I'll just write delta alpha as alpha, because we know that we are dealing with a change in the angle of attack, right? We're not really interested in finding the actual value of alpha, but just how its change is evolving with time. So we'll make this substitution. We'll make this substitution with delta CL written like this. We will get half rho v square s. Now delta CL will be written as dCl d alpha times delta alpha. Now dCl d alpha, we can write it as a shorthand notation, dCl alpha times alpha. Right? So in this way, the moment, okay, or the change in moment depends on the change in the angle of attack, right? So I removed the delta because we are, as I said, dealing with the change, and it's understood. Okay, so not going to overcrowd the text here. All right, I want to know m alpha. I want to know m alpha. But what is this m alpha? Go back. Right, how did we define this? M alpha. This is m alpha. dm d alpha divided by iy. So now I need to find dm d alpha. So dm d alpha is just you differentiate this function with respect to alpha, you will get minus L half rho v square s cl alpha. But I don't want dm d alpha, I want m alpha. So this is equal to dm d alpha divided by iy. So what I really want to calculate is minus L half rho v square s cl alpha divided by iy. Okay, how am I going to do this? L is given to me, it is 0.92 feet. Good. Density, well, it depends on the altitude in which the system is set up. Maybe it is at the sea level, so it's pretty standard. Density is 0.00238 slugs per feet cube in the standard sea level. The velocity square is also not a problem because the value of velocity, let's say, is given to us, and let's say that this is equal to 25 feet per second. So you can find the area as well. So S is also taken care of. Now, what is CL alpha? That is not given to us, right? CL alpha. And what is IY? These are the things that we need to work harder to calculate. So let's start with the easier one, CL alpha. CL alpha is equal to CL alpha. Now, for a thin airfoil, right? So whether it is this or this, doesn't have to be symmetric. We know that the slope is equals to 2 pi. So you find the value of 2 pi, okay? And so you'll have 2 pi divided by 1 plus 2 pi divided by pi. Aspect ratio, you know the aspect ratio of this plate, right? So this is going to be B divided by C. So 1 divided by 0.167. And you will get the slope in terms of, you'll get some number, and this will be in terms of per radian. Okay, because this formula gives you values in units of per radian. So you will obtain this. So that's also taken care of. You can find this. So we really need to discuss how to find IY. Okay, so this is the part which will require some time to be spent. We have discussed the equations for various mass moment of inertia and the product of inertia. These equations are in your notes, and they are also listed as equation 3.20 in the book. The mass moment of inertia about the y-axis is equal to the triple integration of x square plus y square times delta m. This is the general formula, but there are already expressions available for standard geometry. A rectangle is a standard geometry. So for the case that we are dealing with, where we have a plate which has a dimension of length c and a dimension of length b, and this is going to rotate up and down. So this is going to, in some sense, rotate about its y-axis. So let's assume that the forward direction is the x direction, the vertically downward direction is the z direction, so this is the y direction. So this is the pitching motion, so the rotation is about the y-axis. So for this sort of geometry, the mass moment of inertia is given by 1 over 12 times the mass times the square of c square. So first we have to calculate this quantity. Now the mass of the plate and the value of c are both given to us, so this can be calculated. So just to review, the value of c is 0.167 feet, and the mass of the plate is also given. So you can convert this 0.3 pounds to slugs, and you can convert the, well, this is already in terms of feet, so you don't need to convert. So the mass moment of inertia is equal to 1 over 12 times 0.3 pounds, which in terms of slugs will be 9.3 times 10 to the power minus 3 slugs, times the 0.167 feet square. And you can do this calculation and you'll get a number. Okay, so that is the Iy, but this is Iy about the y-axis of this plate, right, which is passing through the center of gravity of this plate. But in this problem, we are interested in the rotational motion about the overall center of gravity, which is not the same as the center of gravity of this plate, of inertia of the plate about the y-axis passing through its center of gravity. But we want the mass moment of inertia about the overall center of gravity. So that can be obtained by applying this equation, Iy. Now this is the mass moment of inertia about the overall center of gravity is equal to Iy prime plus the mass of the plate times d square, where d is the distance between the two centers of gravity. Okay, so you look at the figure. This d is the distance between the CG of the plate and the CG about which you want to calculate the mass moment of inertia. So that will be half 9.3 times 10 to the power minus 3 slugs times 0.167 square, which is already written before and explained before, plus the mass of the plate, which is 9.3 times 10 to the power negative 3 times the distance between the two centers of gravity, so 1 square. So this will give you some number. Okay, so that's the mass moment of inertia of the plate. But this system not only has the plate, it also has the ballast. So you need to update the value of this total mass moment of inertia. Okay, so this will give us the final value of Iy that we need to use for the solution of this m alpha and mq. So this Iy is the overall mass moment of inertia, and it will contain the contributions from both the plate as well as the ballast. So Iy of the plate will be obtained when you calculate this, and this is given as 9.32 times 10 to the power negative 3 slug feet square. So Iy of the plate is 9.32 times 10 to the power negative 3 slug feet square plus Iy of the ballast. Now for the ballast, again you have to multiply the mass of the ballast by the distance between the center of gravity of the ballast and the overall center of gravity. So this distance, 0.5 feet. And the mass of the ballast is also given. You need to convert this to slugs to be consistent with this system of units that we are using. So Iy for the ballast is going to be 1.86 times 10 to the power negative 2 slugs, which is the mass of the ballast, times the square of the distance between the ballast and the pivot and the overall center of gravity. So this will give us Iy equals to 1.4 times 10 to the power negative 2 slug feet. M alpha is equals to minus L. L is 0.92 feet times half times the density 0.00238, okay, 770238, times the speed, which is 25 square, times the area of the plate, which is 0.167 times 1. So 0.167 times 1 times CL alpha. So I left it as it is, but I think if you do the calculation, again, this is pretty standard, you'll get approximately 4.7 per radian. So you can put 4.7 here, divided by Iy. We just wrote the value of Iy. So 1.4 times 10 to the power negative 2. 1.4 times 10 to the power negative 2. So you will get m alpha. Again, you can do the substitution, do the calculations, and according to the reference I have, this m alpha is minus 36.1 per second square. So this is now sufficient for us to calculate the natural frequency. The natural frequency is equals to square root of negative m alpha, as we know from our previous discussion. So this is equals to square root of 36.1, and so omega n will be equal to, or approximately equal to, 6 radians per second. We also want to know the value of the damping ratio, and here is the equation for the damping ratio. But wait a second, that requires us not only the value of m alpha, but also the value of mq. So we need to talk about how we can obtain this mq. So just in general, as you may have seen in the past, if I call this distance, let's say L, and this is r, and this angle is theta, then we know that theta equals to L over r. So L equals to r theta. So dl dt equals to r times d theta dt. So this actually gives us, so if the linear speed is v, then v equals to r omega. So actually I got it the other way around, I think. It should be, this should be the angular speed. And this should be the linear speed. Okay, so the linear speed is equals to r times the angular speed. So the speed by which the center of gravity is moving from its previous location to the new location is given by angular speed, which is the q, okay, that is the component of the angular velocity in the y direction, times the distance between the center and the object, right? So that is equal to L. Okay, so if you refer to the figure here, L is defined as the distance from the center of the circle to the center of gravity, right? So L. So that this speed in the circular path is going to be equal to q times L. That means this angle, which you can think of as the angle of attack, okay, let's call it alpha, the angle between this chord line and the relative wind, right? That's the angle of attack. And this angle of attack can be related to this QL and U naught. Okay, so this is a triangle, and in this triangle I can write tan alpha equals to QL divided by U naught. And when alpha is very small, tan alpha is approximately equal to alpha, so I can write alpha equals to QL divided by U naught, which means now I can make a substitution for this alpha. So I can write m equals to minus L half rho v square s CL alpha QL over U naught. So dm dq will be equal to, okay, so you just notice the q there. So when you take the derivative, you'll get minus L half rho v square s CL alpha L over U naught. So we are now ready to calculate dm dq, and we actually need mq, which is dm dq over iy. But we have the values of all the inputs that are necessary. L is given as 0.92 feet. You can read it from the figure, times 0.5. Density is 0.00238 or 2377, times velocity square is 25 feet square, times the area, which is 0.167 times 1, times CL alpha, which we calculated as 4.7 per radian, times L again, which is 0.92 feet. And you again divided by IY, we have also found the value of IY, that is this. Okay, 1.4 times 10 to the power negative 2. So after you compute, you will get minus 1.38 per second. So now it is straightforward to calculate the value of the damping ratio, and MQ is minus 1.38 per second divided by 2 times square root of negative MQ, which we already know is minus 36.1, but minus and minus will make it positive, so 36.1, and this will come out around 0.115. So in this way you can find the value of both the damping ratio and the natural frequency. So let's note these values first. The values for the two things that we wanted to calculate. So we found that the natural frequency is equal to around 6 radian per second, and we found that the damping ratio is equals to 0.115. The oscillation frequency and the damping ratio are just the required inputs to know how this angle of attack evolves with time. So let's again go back to where all these things came from. These all things came from our attempt to solve a differential equation. So it came from this differential equation, where of course in the simplified equation we don't have this elevator angle, and we don't have the rate of change of angle of attack, but still those simplifications do not have to be applied within the process. Like you can just apply it at the end to the expression that you obtain after solving this more general equation. But what I want to point out is all this work was basically done to find lambda 1 and lambda 2 in this type of expression, because ultimately we want to know how this angle of attack changes with time. We know the oscillation natural frequency, we know the damping ratio, so how does the angle of attack change with time? Okay, so we come back to what we have found and we use our solution for that. So we know that this angle of attack as a function of time, our equation is written for the change in the angle of attack. So that's why instead of writing x as a function of time, I'm writing angle of attack as a function of time, is going to be equal to c1 e to the lambda 1 t plus c2 e to the lambda 2 t plus I omega n square root of 1 minus zeta square, and lambda 2 equals to minus zeta omega n minus I omega n square root of 1 minus zeta square. So just to reduce the clutter, the minus zeta omega n was written as eta, and omega n square root of 1 minus zeta square was written as omega, and this omega was called the damped natural frequency. Damped natural frequency. Okay, so coming back to this solution for the change in angle of attack, this can be written as c1 e lambda 1. So lambda 1 is eta plus I omega. Okay, so that is eta plus I omega plus C2, there is a T, lambda 2, which is eta minus I omega. So e to the power eta minus I omega t. So how can we now know the evolution of the angle of attack with time? That cannot be found until we know the values of C1 and C2. And the values of C1 and C2 can be found from the initial condition. So we need to assume some initial condition in order to actually write this equation in terms of some numbers in the coefficients, some values in the coefficients. So we can, let's say, assume an initial condition. So let's assume that when time equals to 0, the angle of attack was 0. So basically, if this is the bar and this is the rod and this is the plate, let's assume that when time equals to 0, the relative wind is collinear with the rod. Okay, so that this delta alpha equals to 0 when t equals to 0. And let's assume that at this initial time, a gust of wind came and it hit this plate, and the plate started to move at a pitching speed, pitching frequency of 1 degree per second. So let's say that this d delta alpha dt or q, okay, so there are multiple ways of writing this, at t equals to 0 is 1 degree per second, 1 degree per second, which is the same as pi over 180 radians per second, right? So 1 degree is equals to pi over 180 radians per second. So let me again describe the initial condition. Initially, this rod and plate assembly are facing the relative wind such that the relative wind is in the same direction as the rod, so the angle of attack is 0. A gust of wind comes and it hits the plate, and the plate acquires an initial pitching speed of 1 degree per second, or pi over 180 radians per second. So now we have two conditions, so it should be possible to know the value of C1 and C2. Let's do that. So let's apply the first condition, which is at t equals to 0, angle of attack is equal to 0. So we have 0 equals to C1 e eta plus IW 0 plus C2 e eta minus IW 0. So we have 0 equals to C1 plus C2, or C2 equals to minus C1. So this is the first equation we get. Now let's apply the second condition, which applies to the first derivative. So we need to calculate the first derivatives. So d alpha dt is equals to C1 eta plus IW e eta plus IW t plus C2 eta minus IW e eta minus IW t. So when time equals to 0, we know the speed. The speed is pi over 180 radians per second. So pi over 180 equals to, so t equals to 0. So we have C1 eta plus I omega plus C2 eta minus I omega. But we know that C2 equals to negative C1, which we found by applying the first initial condition. So I can pi over 180 equals to C1 eta plus IW. So C2 is minus C1, so minus C1 eta minus IW. Open the brackets, I get C1 eta plus I C1 omega minus C1 eta plus I C1 omega. So these two cancel. And now I have pi over 180 equals to I to C1 omega. So I can solve for the value of C1 now. C1 is equal to pi. 2 times 180 is 360 times omega I. So since I have C1 now, I can know C2. C2 is just a negative of C1, again from what we have found by applying the first initial condition. So C2 is equals to minus of C1, that is minus pi I 360 omega. So we have found the values of C1 and C2. So we are ready to rewrite this equation by substituting for the values of C1 and C2. We can write delta alpha t equals to C1, that is pi divided by I 360 omega e raised to the power eta plus I omega t, and C2 is minus pi I 360 omega e raised to the power eta minus I omega t. Now I can take pi I 360 omega e eta t as the common factor, and inside bracket I have e I omega t minus e negative I omega t. I'm going to multiply and divide by 2i, so I will write this as 2i pi e eta t divided by I 360 omega e I omega t minus e negative I omega t divided by 2i, and this is equal to I and I cancel, so 280. So I get pi e eta t divided by 180 omega, and this expression here is the definition of sine omega t. So this is the equation for alpha that I will get, and we have already solved for the values of eta and omega. So here eta is equals to minus of damping ratio times the natural frequency. So the damping ratio which we obtained was minus 0.115, and omega n was 6 radians per second. And this omega, the damped natural frequency, is equals to the natural frequency times 1 minus damping ratio square. So that is 6 times square root of 1 minus 0.115 square. So let's now see how this appears as a function of time. So in other words, if I am to make a plot of delta alpha as a function of time, then how does the change in angle of attack evolve with time? When does this change in angle of attack go to 0? So let's see that. So to do that, we will have to actually plot this. Okay, so this is how it will behave. So initially, as you can see, when the time is 0, it is parallel to the relative wind. So the angle of attack is 0, and there is a gust of wind which starts the oscillatory motion at a speed of 1 degree per second. So because of this, the oscillation will take place, and the amplitude of oscillation will decay as the time passes, and you can tell that by around 7 seconds or so the oscillation will die away. Okay, so in this way you can characterize the dynamic stability associated with the pure pitch motion of the example that we just discussed.